Okay, it's recording.
Okay, so today we're very happy to have Jonathan Hermon from University of British Columbia, who will talk about random Cayley graphs. Thank you. Please.
Thank you for the invitation, Naomi, and thank you all for waking up early and accommodating me because of the time difference. So this is joint work with Sam Olsker-Taylor. So this is really a massive project that we worked on for 3 years and had various iterations until it got to where it is now. And it's really one of the projects that I enjoyed the most working on. So I'm really excited to share with you the results we have. It's about random Cayley graphs. So we're considering a finite group G. And in this talk, G would be either abelian or nilpotent, almost always. But we really look at the case that we have a sequence of finite groups and their sizes goes to infinity, and we will care about asymptotics result. And the Cayley graph of these groups, we're going to consider them with respect to random sets of generators. So we call it a Cayley graph of a group G with respect to some generators Z1 up to Zk. Is just the graph whose vertex sets are the elements of the group, and we draw an edge between two elements if we can get from one to the other via right multiplication by a generator or an inverse of a generator. We can also consider the Cayley D graph where we don't take the inverses. Okay, but in this talk, I will not talk about the digraphs. K throughout the talk is going to be the number of generators. And we're going to denote them by Z1 up to Zk, and they will be uniformly chosen at random from G. And they're going to be IID uniform on G. Because we actually have a sequence of groups, then K is actually a sequence that depends on the size of the group. And we're going to pick K such that it's going to diverge. And later I will explain why this is necessary for us. And we're also going to take K such that log K is of smaller order than log size of the group. And I'm also going to explain why we need that assumption later on. So in particular, K is number of generators K is much smaller than log square root size of the group. And this really tells us that there is no difference between sampling with replacement, the generators, or without replacement. Okay, so even though we pick them IID uniform, so with replacement, it's like picking without replacement, which is essentially saying like we're picking the Cayley graph with K generators uniformly at random. Okay. So it is a natural model in that sense. There's an abuse of terminology because I will call Z1 to Zk the generators, but I'm not conditioning on the event that they generate the group. But in the setups that we will consider, in particular, we will show that with high probability, they generate the group. Okay, so even though I'm not conditioning on this, I will call them generators. Okay, so we will denote this random Cayley graph by G sub K. And even though all our results also work for the digraph, in this talk, maybe with different constants, in this talk, we only talk about the Cayley graph. So I want to emphasize that the group is not random. That's a completely different type of question. What is a random group? What's a good way of sampling it? And how it behaves. Here G is given, or the sequence of groups G is given, but the choice of generators, or what Cayley graph we're picking, that's the randomness. Okay. So, to motivate the model, this is really an instant of the general question: how does a generic random element in a certain family of object looks like or behaves like? And studying these type of things really goes back to the pioneering work of Erdős and Renyi about random graphs. But this type of questions have been studied extensively in many contexts. So what we want to show is to establish certain universal properties of random walks on such graphs and the geometry of such graphs. And by universality, I mean that it's properties that don't really depend on the group in some way. And in some way, just depends on the size of the group and the number of generators. And this is really motivated by a conjecture of Aldos and Diaconis from their seminal 86 paper, in which they coined the term cutoff. And they conjectured that simple random walk on a random Cayley graph with K generators always exhibits cutoff, which I will define later, but what it means loosely is that it converges very abruptly to equilibrium for a K which is large. And not only is there cutoff, the cutoff time is independent of the algebraic structure of the group. So it's just a function of the size of the group and the number of generators. Okay, and this is a remarkable conjecture because they made it so early on in the study of mixing times even, in particular the cutoff phenomena. And this generated a lot of research, and the conjecture is in many ways is true, as you will see. So sort of one celebrated results about random Cayley graph is the Alon-Roisman theorem, which tells you that for all groups, if we take the number of generators K to be at least logarithmic in the size of the group, then with high probability we get an expander. So we can make the Chigel constant arbitrarily close to 1 by picking this constant here to be large enough in terms of epsilon. And equivalently, by Chigger's inequality, it means that the spectral gap is bounded away from 0 and can be made arbitrarily close to 1 as well by taking C large. So here the spectral gap is the second smallest eigenvalue of the Laplacian. So the identity matrix minus the transition matrix of the simple random walk. So in the abelian case, we extend this result to smaller values of K, so smaller than logarithmic. And we show that generally, if K is a bit larger than the minimal size of a set of generators. So DG, you can think about it as the dimension of the abelian group. So it's the minimal size of a set that generates the group. So if K is a bit larger than that, so delta is an arbitrary constant, we determine the order of the spectral gap. So it's a 1 over the size of the group to the power 2 over K. So the exact expression is not very important, but in particular, we see that this vanishes when K is of smaller order than log size of the group. Okay, so we don't get an expander if K is smaller than logarithmic. Okay. Okay, but this refines to a certain degree the Alon-Roisman theorem. In particular, it allows you in many cases to say something even when K is epsilon times log n. Okay, so it's a certain refinement. So if you're interested, you can read later this more precise statement. So I slightly cheated the way I phrased it. It's not very important. So one open question is, when G is not abelian, does the random Cayley graph becomes an expander with high probability for smaller values of K, so smaller than logarithmic? One particular formulation can be, maybe it's enough for K to be logarithmic, not in the size of the group, but in the size of the abelization of the group, where for a group G, the abelization is the quotient G divided by the mod the commutator subgroup. So this is always an abelian group. It's the largest abelian quotient of G. In particular, this would imply that when we look at the symmetric group, then for order 1 generators, we already have with high probability that GK is an expander. Right? And this is a major open problem, the case that G is equal to the symmetric group. And this is really pushing things as far away from what I'll be talking about today, which is the abelian case and a bit the nilpotent case. So sort of the state of the art on the case of the symmetric group is due to Elfgott, Seres, and Zuk, and that for 2 generators with high probability, GK is connected. And they also have a bound on the mixing time. So another type of question about the geometry of the random Cayley graph is about the diameter. And here the state of the art is due to Shapira and Zuk, a different Zuk with different spelling. And what they show essentially is that if the dimension D and the number of generator K are fixed, then the diameter, first of all, the order of the diameter behaves like a K-dimensional torus of equal side length. That's sort of the way to interpret the scaling we see here. And moreover, there's a distributional limit. And they give a semi-explicit description of this distributional limit. This resolves affirmatively a conjecture of Benjamini. And I want to mention that there are earlier results, in particular, the first result, it's for the case of a cyclic group of prime order, and this is due to Amir and Gural-Gurevich. And there are some, so a recent result about some nilpotent groups, and in particular, the case of D by D unit upper triangular matrices with integer entries mod M. So this group will come up a lot in this talk, and I will denote it by U for upper triangular, MD, where D is the dimension. So they show a certain extension of this result with the same distributional limit, but instead of taking here the size of the group, the relevant thing is the size of the abelization. Okay, so this actually resolved the question that Sam and I asked in our paper. And this theme of replacing the size of the group by the size of the abelization will repeat itself in this talk, in the nilpotent case. Okay, so we also have some results about diameter and more generally about what I call typical distance. So for abelian groups, we showed that if the number of generators is a bit larger than the dimension and the number of generators diverges, then with high probability, the typical distance from the identity in the random Cayley graph is concentrated. So what this means is that all but a negligible fraction of the vertices lie in a thin shell around the origin. This shell has radius roughly R, uppercase R, and this R usually has this simple description. So it's the minimal radius of a ball in Z to the K that has size at least the cardinality of the group. Okay, so this is weaker than the results about diameter because this just tells you about what most vertices do, but it doesn't tell you the diameter. But if K is at least logarithmic, it actually gives you, we actually improve this to obtain the same thing for the diameter. Okay, so far I talked about things that are easy to define, like the spectral gap and the diameter. But now I want to go to sort of the main event, which is mixing times and cutoff. And for this, I need some definitions. So first of all, we need to pick our notion of distance between distributions, and this is going to be the total variation distance. So if we think about mu and nu as row vectors, this is just half the L1 distance. Okay. So these are going to be distributions on this finite group G. And then we can define the epsilon total variation mixing time of a Markov chain, xt, to be, so we denote it by t mix epsilon, and this is just the first time t, such that the distribution at time t of the Markov chain as a total variation distance at most epsilon from the stationary distribution of the chain. Okay, and we want this to hold for all initial states x. But in our case, we're going to look at random walks on Cayley graphs. So by symmetry, it doesn't matter what is the initial point of the walk, and we're going to take it to be the identity. Okay. Okay, now we have the notion of mixing time, and the next notion is cutoff. And we say that a sequence of Markov chains exhibit cutoff. So loosely speaking, it means that the epsilon mixing time is independent of epsilon asymptotically. But what I mean by that is that the ratio of the epsilon and 1 minus epsilon mixing time tends to 1 as n goes to infinity, where n here is the index of the chain, right? Because we have a sequence of chains. Okay, so this makes sense when we talk about a given sequence of Markov chains, but we're going to look at random Markov chains because we're looking at random walks on random Cayley graphs. So we're going to talk about a slightly weaker notion of cutoff. We're going to talk about cutoff with high probability, which just means that equation 1 holds in probability. Okay, so the ratio converges in probability to 1. Okay, are there any questions about this definition? So I'm going to show you now a graphical representation. So when cutoff occurs, the graph of the worst case distance from equilibrium as a function of time asymptotically looks like a step function that drops very abruptly from near 1, which is the maximal value for this total variation distance, to near 0. And it happens at a narrow time interval, which is referred to as the cutoff window. And the width of the cutoff window, so this is, roughly the short interval here, is much smaller than the length of this interval between time 0 and the time that the curve starts dropping abruptly. Okay, so that's really what cutoff means. It's this graph. And the superscript n means that this is for the nth chain in the sequence. Okay, so many families of Markov chains exhibit cutoff. So many are believed to exhibit cutoff, but fairly few examples are fully understood. And one motivation for proving cutoff is that in order to prove cutoff, we really have to understand the family of Markov chains that we're considering very, very finely. So we get a very complete picture of it, because essentially, and sometimes quite literally, we identify what is the bottleneck for mixing. Okay. And doing so often involves developing new ideas that end up being useful for various setups. So here I just wrote 3 examples that came to mind for me a few hours before this talk. I'll just mention one today because it's going to be very relevant for this talk. And this is the entropic time paradigm, which is due to Berestiki, Lubetsky, Peres, and Sly in a paper that I'll mention in a second. And it's also fair to mention that a major contribution to developing this method is due to Sales and his collaborators. Okay, so a recurring theme in the study of cutoff is that random instances often exhibit cutoff. So like in our case, looking at a sequence of random Markov chains sampled in some canonical natural way often give rise to cutoff, or cutoff with high probability. And moreover, the cutoff time usually occurs around a certain entropic time. And usually what this means is that we're going to look at a certain auxiliary Markov chain. Okay, and usually it's going to be the random walk on the Benjamini-Schramm limit. Okay, in our case today, it's not going to be quite the Benjamini-Schramm limit, but in some sense, it's close to the Benjamini-Schramm limit. And the entropic time is then the time in which the entropy of the auxiliary Markov chain is equal to the entropy of the stationary distribution of the finite Markov chain. Okay, and you know, by now, this is really a paradigm, and many instances of this have been developed, and I'm going to give you a partial list. And it really seems like using recent developments, this can actually push to much other examples that have still not been verified. So here's a partial list of cases in which this paradigm was verified. So the Berestiki-Lubetsky-Peresly paper is about the case that the random graph is the giant component of an Erdős-Renyi graph, and also the configuration model with minimal degree at least 3. Then Bordenave, Caputo, and Sales proved this for a random digraph with a given degree sequence. So what's remarkable about that case is that this is not a reversible Markov chain, and there isn't quite a, you know, the stationary distribution is not very well understood. But even without knowing the stationary distribution, they were able to prove cutoff at the entropic time. Another notable example is Bordenave and Laquan, who proved cutoff for random walk on a random n-lift of a certain graph, of a certain base graph. When I say certain, I mean an arbitrary, I guess connected. And then the last example I want to mention is a joint work with Sly and Susi. And this is a very sort of generic operation on a given graph. And we call this construction a quasi-random graph. So you start with an arbitrary bounded degree graph, or a sequence of bounded degree graphs. And we don't even need them to be connected. We just need the connected components to be of size at least 3. And then we do the following smoothing operation. So we keep the initial structure, but we are adding new edges at random according to a random perfect matching of the vertices. So we take a perfect matching of the vertices at random, and for each pair that is matched, we draw an edge between them. So it turns out that, first of all, with high probability, we're getting an expander. And moreover, there's cutoff at an entropic time. Okay, so I do want to point out that this is the only example so far that the Benjamini-Schramm limit is not locally tree-like. Sorry, the Benjamini-Schramm limit is not a tree. So the random graph is not tree-like. Yeah, okay, so the work I will present today is yet another example of this cutoff at the entropic time paradigm. So we prove cutoff at the entropic at a certain entropic time that I will define more precisely later on. So when G is a billion, all we need to assume is that the number of generators K minus the dimension D diverges. So usually, just so you have a concrete idea, so usually the entropic time will just be the time in which the random walk on Z to the K as entropy log size of the group. Okay, so Z to the K is not really the Benjamini-Schramm limit because K diverges. So there isn't a Benjamini-Schramm limit, but in a sense, it's the right object to look at to have that sort of in the local topology, this is close to the finite graph we're looking at. Okay, so Z to the K here is a canonical object. It's the free abelian group with K generators. So notice that this cutoff time, this entropic time, when it agrees with this description I gave you, is just a function of the number of generators and the size of the group. So this agrees with Aldos Diakonis's conjecture. So we also have results for the group of unit upper triangular matrices. Here the dimension is fixed or diverges slowly, and M is the thing that goes to infinity. So the entries are defined mod M. But here the entropic time is defined in terms of log of the abelization. Okay, so I have two comments about this. So you could have guessed that actually the right generalization from the abelian case is to generalize zk to the corresponding thing. So zk is the free abelian group with k generators. So the corresponding thing should be the free nilpotent group of step d minus 1 with k generators. Okay, but if you look at this generalization, then you're actually overshooting the mixing time. So this is not the right thing to look at. Moreover, this entropic time that I just defined also depends on the dimension. So here the cutoff time does depend on the algebraic structure, okay, as opposed to the secondary aspect of the Aldous Diaconis' conjecture. So there's still cutoff, which is really the main point of their conjecture, but it could depend on the algebraic structure already for nilpotent groups. Okay, so recall that what the Aldous Diaconis' conjecture says is that GK exhibit cutoff as the size of the group diverges when K is large. More specifically, when K is of larger order than log number of generators. Okay, and sort of the first progress on that is due to I guess Do. And he confirmed this conjecture when K is a super polylogarithmic. Okay, and not only is there cutoff, it happens around the fastest possible time, which we often call in the mixing time community the diameter lower bound on the mixing time. So it's a log size of the graph, or size of the group in this case, to the base number of generators. Okay, so it would be useful moving forward to give you a certain certain simple description of how we can generate the random walk on the Cayley graph. And we sort of think about it as happening in two steps. So let ST be the random walk on the random Cayley graph. And we can think about it as, first of all, we sample a random word, WT, in the free group. So it's either the free group, and this is only going to be relevant for non-abelian groups, or it's going to be the free abelian group, Z to the K. Okay, so we first take this word in the free group, and then we substitute the generators. Okay, so what's good about that? It sort of allows us to deal with two sorts of randomness separately. There's the randomness coming from the choice of W and the randomness coming from the choice of generators. Okay, so the way to think about W is just as a list of the sequence of indices picked in the order they're picked and with the sign that they are picked. Okay, but in the focus of today's talk, we're looking at the abelian case, and all the information we care about is how many times did we pick Zi minus how many times we pick the inverse of Zi. So we're going to define Wi to be this discrepancy in the number of times we picked Zi and the inverse. Okay, and when we do that, we just get that W is a simple random walk in continuous time on Z to the K. Okay, so W encodes the information of how many times we picked each generator minus the inverse of the generator. Are there any questions about this? Okay, so sort of the next thing I need in preparation is to discuss L2 distances. So it's often the case that it's nicer to work with second moments, or in our case here, it's L2 distance instead of total variation distance, which is essentially L1 distance. So the L2 distance square of a distribution mu on G from the uniform distribution on the group pi. So it's really what it should be. Instead of having absolute value like in total variation, we're taking the square, but we have this normalization by the size of the group. And the reason we have this normalization is that by Cauchy-Schwarz, this is larger than the total variation distance. Okay. And then sort of a one-liner elementary algebraic manipulation, basically opening the square. It tells us that the L2 distance square plus 1 has this very compact form. So it's the size of the group times the sum over all elements of the group, mu of G square. Okay, so we would want to show that the right-hand side is small. Is roughly 1, is 1 plus little of 1, in order to show that the mu is very close to pi. Okay, so here's why it's very convenient to work with the L2 distance. So if ST, again, is the random walk on the random Cayley graph, and now we're looking at the independent copy of the random walk, but it's independent given the graph, i.e. given the generators. Then using the formula we obtained for a general mu, we can say that the L2 distance square plus 1 is equal to, so we just substitute for mu this distribution. And that's what we do here, and we have a square, like we have here a square. But because S prime is the independent copy, we can write the probability that ST is equal to the element G as the probability that both ST and S prime of T are equal to G. And then we get rid of the square. And then instead of summing over all elements, we just see that this is equal to the probability that S is equal to S prime. Right, and all this is given the graph, given the choice of generators. Okay, so we derived this nice expression. Now let's take expectation and see what happens. Okay, we take expectation, and here we had this quantity given G, and now we get rid of it. Okay, so let's see what happened. So here on the left-hand side, inside the expectation, we're looking at a quenched L2 distance square. But then in the right-hand side, we have an annealed probability. So we're averaging not only over S and S prime, but also over the choice of generators. Okay, now this should look suspicious. Right, it looks like we're cheating because, if we're able to show that the right-hand side is little of 1, then it follows that the expectation on the left-hand side is little of 1, and then by Markov's inequality, we get that with high probability over Z, over the choice of the graph, the L2 distance at this time t would be also little of 1. Okay, and then you shouldn't be able to say something intelligent about a quenched thing using an annealed calculation. Usually, that feels suspicious. And the reason there's not really a moral contradiction is that the quantity on the right-hand side, the time t for which it's small, is not really the mixing time. And usually it's of a larger order than the mixing time. And this essentially is because L2 distances can blow up due to rare events. Okay, and this is exactly the same reason for which second moments can blow up because of rare events. Okay, and the way to often get around this for second moments calculation is to do a modified L2 second moment calculation. And likewise, here we will do a modified second moment, sorry, a modified L2 calculation. Okay, so the modified L2 calculation will involve conditioning on W and W prime, right, which are in the abelian case just how many times each generator was picked for S and how many times each generator was picked for S prime with cancellations, to both behave typically, so to satisfy some good conditions that hold with high probability anyway. So it's sort of harmless for us to condition on this to happen. Okay, so for instance, one example that is not going to be relevant for the results in this talk is that there is some generator, Zi, that is picked only once in W and 0 times in W prime or vice versa. So for instance, assume that this happens. Then if this happens, we will have that S inverse times S prime is uniformly distributed on the group, right? The reason that this is uniformly distributed is that it's going to be equal to some A times Zi or Zi inverse times B, where A and B don't involve Zi. Those are independent of Zi. Okay, and when you have something like that, this is going to be uniformly distributed because Zi is uniformly distributed. Okay, so sort of on this event, we will get that the probability that S is equal to S prime is going to be 1 over the size of the group. All right, this is like saying that it's uniformly distributed, the quantity here. Okay, but if this probability is equal to 1 over G, sort of substitute here 1 over the size of the group, and we get that the quantity we want to show is small is equal to 0. Okay, so this is just sort of a warm-up, but this very simple example, this leads to a strategy which actually recovers quite easily the Alon Roisman result, and it also recovers Dawes result, so verifying the Aldous Diaconis conjecture when K is super polylogarithmic. Okay, so both of these proofs are one slide, and I included them in the slide, so you can look at it later if you're interested. Okay, so far I just told you what the modified L2 calculation would involve, but let me tell you how, what bound it gives us. So instead of looking as before on the expected L2 distance squared, we now look at the total variation distance squared. Okay, and then the first quantity, so this quantity right here is going to be what we had before, but with the additional conditioning that W and W prime are nice. They satisfy some typicality conditions that we will have freedom to pick. And then this additional error term, which is the probability that W is not typical. Okay, and we will always pick tip such that this probability is going to be little of 1. Okay, so tip is an event that depends on this random walk on Z to the K. Okay, so I'm gonna skip this proof, but it's very similar to the proof we had before. It's a certain Cauchy-Schwarz. And here are the, that's Dawes result. And this is Alon Roisman. So both of them are quite short using this observation. Okay, so here are some additional previous results. So Dow and Ildenberg confirmed, sorry, they proved cutoff in the abelian case when K is a larger order than log n. Okay, and then later Wilson, so that was the first case, the paper of Wilson, when cutoff was proved when K is also logarithmic in the size of the group. So he considered the case that the group is Z mod 2Z to the D. And he basically proved the best possible result. So he showed that conditioned on the group being generated, then with high probability there's cutoff. Okay. So in that work, he also conjectured that this group that he considered is the slowest mixing group. So it's the slowest mixing group for a random Cayley graph. And this is in a very strong sense. So for all groups G of size at most 2 to the D, he conjectured that for all values of K, number of generators, with high probability, the mixing time of GK is smaller up to smaller order terms in the limit, they vanish, than the corresponding mixing time when we look at the group Z mod 2Z to the D. Okay. And sort of a breakthrough, which was the first case in which cutoff was proved in the case that K is smaller than log size of the group. This is due to a hoof, and that's a recent result. And this is for the case of cyclic group of prime order. Okay, but sort of because of the philosophy I showed you before, that you can prove cutoff quite easily when there's a generator that is only going to be picked once. So actually this happens with high probability, this scenario, when K is of larger order than log N. Okay, so this sort of is quite useful for proving cutoff. And you know, the case that K is of smaller order than log N is much harder because typically each generator is going to be picked many times. Okay, so one of our results is that we verify Wilson's conjecture, but we verify it only for nilpotent groups. Okay, so for nilpotent group, indeed, Z mod 2Z to the D is the slowest mixing in the sense that Wilson conjectured. So some comments about the proof is that, first of all, we have a comparison argument between the mixing time for a random Cayley graph when G is a nilpotent group and a corresponding abelian group of the same size. And using this comparison argument, we only need to consider abelian groups and verify the conjecture for abelian groups. So this comparison argument actually gives us cutoff for many nilpotent groups for free. But it gives us cutoff when K is at least logarithmic only with this specific argument. And I don't want to give an exhausting list, but for those of you who are familiar with the notion, in particular, this is the case for extra special P groups. And if you don't know what they are, it really doesn't matter. Okay, so we reduce things to the abelian case. And in the abelian case, we can just read off the result from our cutoff result. Because our cutoff result in the abelian case actually gives us an abstract description of the cutoff time as an entropic time. And we can verify that the entropic time for a given size of a group is maximized by the group Z mod 2Z to the D. Okay, so recall the setup in the abelian case. W encodes how many times we picked Zi minus how many times we picked the inverse up to time t. So basically every time we pick Zi, we add 1 to the ith coordinate, and every time we pick minus Zi, we subtract 1. And then the random walk can just be written as the sum Wi times Zi. Okay. So I want to define the entropic time, and the main term in the entropic time is this quantity I described to you before, T0, which is the time in which the entropy of a random walk on Z to the K equals log N. n is the size of the group. Okay, so this is the main thing to keep in mind. And then there's these other things that are sort of complicated and they're usually not important. Okay, and we can determine the asymptotic of this. This is not very important. So the other quantities, Tm, is the time in which the entropy of simple random walk on z mod mz to the k is equal to log of the group G mod mg. Okay, where m is an integer, and mg is just multiplying each element of the group by m, which makes sense because it's an abelian group. Right, but given the composition of G to a sum of cyclic group, it's very easy to say what mg is. Okay, so finally, the entropic time uppercase T is obtained by taking the maximum of T0 and Tm, where m divides the size of the group. Okay, and if this definition of Tm is a bit much for you, it's fine, because really T0 is the main thing to remember. Okay, so recall that we assume that the number of generators diverge, but log number of generators is little o log size of the group. And here's why. So for nilpotent groups, it follows from a classical result of Diaconis and Saloff-Cost that if the number of generators is order 1, then deterministically for all choice of generators, there is no cutoff. Moreover, for all groups, not only nilpotent, if log k is of order log n, then the mixing time is of order 1 and there's no cutoff. Right, so if we want to prove cutoff, we need this assumption on k. And again, this is the dimension. So the result is as stated before. There is cutoff at the entropic time that I just defined whenever number of generators minus the dimension diverges. So under very mild conditions, so typically this entropic time is just T0. Okay, T0, again, time at which the entropy of the random walk on z to the k equals log n. So an example for mild conditions is k being at least 1 plus a constant, the dimension. Or for instance, we don't need to assume anything in addition if k is not too large in terms of size of the group. Yeah, I'll skip the next comment. Okay, so I already told you what is the result for the group of unit upper triangular matrices, and it's sort of the same thing, but here the entropic time is defined with respect to the abelization. I don't really have time to discuss this, but I do want to sort of say a few things. So the reason it's interesting to look at this group is that it's a canonical example of a nilpotent group. And when the dimension is 3, this is just the Eisenberg group. So this, in the random walk community, has served as the canonical example of a nilpotent group to study the behavior of a random walk on. But this was done in the case of a canonical choice of generators, whereas we're looking at the, the typical case, a random set of generators. But actually, even though we weren't aware of it at the time, our argument actually, a lot of it extends to general nilpotent groups of bounded step. And this is really due to observations that were given to us by Peter Vario. And sort of, it's nice that some representation theory comes into the story, where in the results that I present today, we don't need to use representation theory. Okay, so I'm going to give you a quick sketch proof in the 5 to 10 minutes that I'll take. In addition, so I first want to remind you the notion of entropy of a distribution mu. So if X is distributed like mu, the entropy can be written as minus the expectation of log mu X. Now, if we take X to be WT, so a random walk on Z to the K, the different coordinates are IID. So because of that, this log is going to factorize into a sum of IIDs. So here nu is the law of each of these coordinates. So it's a random walk on Z with rate 1/k, evaluated at time t. Okay, so we want to take expectation of this, but right now this is a random variable, and because we wrote it as a sum of IIDs and k diverges, we should expect that there's a CLT. So this should be concentrated around the mean, and the mean is the entropy we care about. Okay, so we're going to leverage that. So we want to show the lower bound on the mixing time. So what that means is that shortly before the entropic time, the walk is far from being uniform or far from mixed. So the total variation distance is 1 minus little o of 1. And we're going to consider a time t minus, which is slightly smaller than t0, the entropic time. Okay, and we're going to prove this for some choice of little o of 1 terms. So a calculation which is not very fun shows you that if we change the time t a little bit around the entropic time, we can actually change the entropy a lot. So we change the expectation of this random variable a lot, and a lot means by a diverging additive term. But not only a diverging additive term, this additive term is going to dominate the typical fluctuations of the random variable whose mean is the entropy. Okay, more than that, we also verified that the typical value of the fluctuations doesn't really depend on t, provided that t is close to the entropic time t0. Okay. So if you believe this, then you know that there's going to be some little o1 term such that shortly before the entropic time, time t0, or here t should be, sorry, t minus, here t should be t minus. There's some diverging term omega such that with high probability, log n minus log mu of wt is at least 2 omega, okay? So this holds with high probability, and from this you can read that with high probability, mu of wt, okay, mu is the law of wt, is at least e to the omega over n, right? This is implied by this. Okay, so I'm saying that this almost immediately implies the lower bound on the mixing time. And even though it's very elementary, it seems that this idea was not didn't appear in the literature before. Okay, so I'll explain why this implies a lower bound on the mixing time. Okay, so we're here. So on this high probability event that this holds, WT has to belong to a set which has cardinality at most the inverse of this lower bound. Okay, and because omega diverges, this set is of size little o, size of the group. And this is simply because if we have a set and some distribution that gives each point probability at least p, then the size of the set can be at most 1/p. Okay, so on a high probability event, WT is supported on a tiny set. But our random walk is a projection of WT. So the random walk on this event is even supported on a smaller set, right? So, and this is true for all choice of generator Z. So for all choice of generator Z, we see that the random walk will not be mixed shortly before the entropic time. Okay, so this sort of philosophically, I feel like this should be sort of convincing and quite simple. the upper bound on the mixing time is a bit more involved. And I see that I sort of ran a bit over time. Yeah, okay, so I'm not going to say anything about that, but there was also this entropic times depending on M, and sort of one can repeat this argument and work a bit harder and also derive a lower bound for these quantities Tm. I'm going to skip that. Okay, so I have two things that I want to show you, which I might just concentrate on one. So this is a warm-up, and this is a proof in one slide. When we look at the group Z mod P, sorry, we look at a abelian P group. So the group ZP to the power D. So one option is for me to give you this one slide proof in this case. And then the other thing is a sketch proof of how to treat general abelian groups. Okay, I think it's more reasonable for me to just give the case of P groups, given the time. Okay, so here we're looking at the time T, which is slightly larger than TP. So TP in this case is the time in which the entropy of simple random walk on Z mod PZ to the K is log size of the group. So log P to the D. Okay, and we're going to write W instead of WT just to make things look better. So here the set, the typical set is going to be all lowercase w in Z to the K, such that the probability that uppercase W is equal to lowercase w mod P is at most some delta, where delta is little o of size of the group. Okay, so the same reasoning about the concentration of the object around the entropy can now be used in the other direction to tell you that because we're looking at a time slightly larger than the entropic time, we can pick some delta, which is little o of 1 over the size of the group, for which this is a typical event. Okay, W mod P will typically have a value that has probability much smaller than 1 over n. Okay, so this is what written here. So, you know, we can pick the little o1 terms and delta as written here, such that this is a typical event. So recall S is Wi Zi, sum over I, and S prime is the same with Wi, W prime, which is an independent copy of W. So let's consider what happens when W is not equal to W prime mod P. And I claim that in this case, S minus S prime is uniformly distributed on the group. Okay. So here's why it's uniformly distributed. So this is doesn't assume the group being abelian. So if A is coprime to the size of the group, the operation of sending an element to the 8th power of the element is invertible. Okay, this is always the case. So in our case, if W is not equal to W prime mod P, then when we look at the difference S prime, there's going to be one term Zi that appears with a power or with a constant next to it, which is coprime to the size of the group. Right? And just having this term would make the difference S minus S prime being uniformly distributed. Okay, so let's explore what this means. So this thing, which is the quantity we want to show is little o of 1 to obtain an upper bound on the mixing time, is now reduced to n times the probability that W is equal to W prime mod P, conditioned on typicality. because if W is not equal to W prime, we get here we get a contribution of 1 over n. We multiply by n, and this is cancelled with the -1. Okay, but we're good, because by definition of typicality, we see that this probability is at most delta. And delta is little o of 1 over n. So we win. So this is little o of 1. Okay, so the moral is P groups are really, really easy for the abelian case. And we have to work much harder for non-abelian groups. But unfortunately, if you're interested, you would have to just look at the slides after the talk. Yeah, thank you very much for your attention.
Thank you, Nathan. Thank you for a very nice talk. Are there any questions?
So just to set the intuition, I mean, so if you take the one-dimensional torus, I guess that the diameter result is easy to get, right? If you get
what,
one,
the scaling limit, or the order of it, or the exact
order.
constant?
No, at least the order.
Okay, I mean,
just by partition, right? You take 0, which edges come out of it. If you get right n over 2, then you already diameter is already cut to n over 4, etc. So I think you can do this.
Okay, so like I said, that's the first result. Even the result was under the case that it's a cyclic group of prime order due to Gidi and Ori. And the paper is short and the argument is very elegant, but it's not trivial. I wouldn't say it's easy. It's easy once you see the proof. I don't know. I don't know how hard it is to turn your intuition into a proof, I would say. Are you saying that one direction?
No. So I guess my question is, at least this is intuitively clear to me. Is it easy to explain the intuition of the cutoff result for one simple case? That's my question, I guess.
Well, given how simple is the argument for abelian P groups, then that's sort of part of it. Yeah, I think I can try to say something. We have this modified L2 distance that we want to control. So rho is this thing where W and W prime has to be typical. And we can split it into two contributions. And the first one is that W is literally equal to W prime. In this case, we're screwed. S is going to be equal to S prime. And this is really the quantity that we show it dominates the total variation distance. Like inside the cutoff window, this is the main term. And then we need to control the probability that S is equal to S prime when we also have the conditioning that W is not equal to W prime. And sort of here something interesting is going on. And I'm not going to go through the proof with you, but the thing we're averaging over is the GCD of this vector Wi minus Wi prime running over all I and n. Okay, so we're looking at this GCD, and the main observation is that S minus S prime is going to be uniformly distributed on the subgroup GCD times the group. And this really tells us a lot. It tells us that the probability that S is going to be equal to S prime given this GCD is equal to the size, is equal to 1 over this group. Okay, and we have the size of the group is this thing that we have here. So we're getting this ratio, and this is not enough always, but sort of often it's enough to use this very naive bound that this thing that we want to control and show that it's close to 1 is at most the GCD to the power the dimension. So, this can be a costly term, but what's really the probability that the GCD obtain a certain value? So the probability that the GCD obtain a certain value, we can upper bound it. So the value, let's say L, we can upper bound it by the probability that L divides all of the entries, divides all of Wi minus W prime I for all I. But these are IIDs, right? So the probability that it's going to divide all of them is the probability that it divides one of them to the power K. And essentially, this probability is at most 1 over L. It's essentially equal to 1 over L. And that's actually a very sort of neat part of the argument. But if you sort of want to see why that is, you can review the slides after the talk. So we're going to get here 1 over L to the power K, right? But K is larger than the dimension. And if K is sufficiently larger than the dimension, this is enough. But if K is very close to the dimension, you have to actually be more careful. And this very brutal bound here, you have to do better than it when K is close to the dimension. And it took us a really long time to figure out how to do that.
Thanks.
So thank you for accommodating, giving a full sketch proof, even if that was not your intention.
Any other questions or comments? So I wanted to ask, it seems that if I understood correctly, you succeed to get the cutoff phenomena from concentration phenomena, actually, right? From concentration, you were talking about concentration of the entropy. And this seems like some kind of CLT, as you were saying, some very general thing. So yes, so is it also, it's like for intuition also for to understand, is it really like a connection, concentration of entropy?
Yeah, that's
when
a
people
really,
say
really
yes,
good question.
Mm-hmm.
So I would say that that's sort of a refinement of the paradigm that I described of cutoff at the entropic time. And recently, this has been extended to some Markov chains which are not random. And one case is a new proof for cutoff for Ramanujan graphs. And unfortunately, I forgot the name of the author. And sort of a newer result is about Markov chains with a non-negative curvature, and this is a result of Sales, and he used exactly this idea. Used the quantity called the var entropy, and basically as a general result about concentration. How concentration phenomena implies of something that its mean is the entropy, how that implies cutoff, and then he was able to use this general result to show that under some natural conditions, a non-negative curvature implies cutoff. And that's actually something that was conjectured by, a stronger and more general result was conjectured by Peres and Tetali. But in all of the previous results about cutoff for random graphs, random walks on random graphs, this has really have been the underlying thing. And in this first seminal work on the Erdős-Renyi and the configuration model, that's a lot of what they did. So it's sort of classical, all these ergodic theory results about entropy on random walks on Galton-Watson tree, which is the Benjamin-Schramm limit. But they sort of had to prove much more refined results about concentration of the random variable whose mean is the entropy.
I see.
And in other works as well, including basically all the results in the list I gave uses this, but it sort of took a while, and I can give this credit to Justin Sales, that sort of he sort of was able to see this paradigm more clearly and
yes,
sort of articulate it very well. Yeah.
It seems like underneath there is there is somehow a need and the connection between these, right? You were able to draw cutoff phenomena from that. So that's very nice.
So if you're interested, Justin writes papers extremely well, and his paper that I mentioned is recent, and it's like 15 pages or 18 pages, but it's a very smooth read. I think even maybe less than 15 pages. So yeah, I highly recommend having a look if you're interested.
Yes. Any other comments? Okay, if not, then we thank Jonathan very much again for the very nice talk and results, and for staying up late for us. Stay tuned, we'll meet next week. And I think it is an afternoon talk, but we'll send an announcement in the beginning of the week. See you all.
תודה, יונתן.